Hi, my name is Eric, and welcome to this series of Electronics for Makers. This is a series of videos for people interested in electronics, but that don't know the building blocks of many of these things. The idea is that we can learn it in a fast, simple to understand, yet useful way. Okay? And how we're gonna do that? First of all, our method is gonna be simple. Every lesson, every video, we're gonna see some sort of law, some sort of principle that we can always refer to when analyzing something and trying to solve a problem. And it's gonna be these principles, these guidelines, they will be used as guidelines that will carry us on throughout the course. Okay. Now, the way I see it, first of all, everything new student needs to learn about electronics, electricity in general, is these four basic concepts, in my opinion. Learning this, understanding all the other stuff is going to be extremely simple. Okay. The first of these concepts we're going to explore is current, the concept of electrical current. What is electric current? In a physical level, it's basically charged particles, whatever kind of particles we have, flowing through a conductor in an orderly fashion. You know, this is the key word, an orderly fashion. Okay, so in this conductor, this flow can happen in any type of conductor. It can be a piece of copper wire, it can be some kind of chemical solution, it can be air, ionized air at least. Like, let me just change the color of my ink. For example, when you have some clouds in the sky and you have lightning, this is a flow of current. The lightning is a flow of current. The air becomes ionized, and ionized air conducts electricity, is a conductor of electricity. In liquids can be some chemical solution, this way, where you have some kind of liquid. Let's change the color again to, I don't know. You have a liquid here of some sort, some kind of element, and this is a good conductor of electricity too. The ions in this solution can carry electric particles. But for the sake of simplicity, we're going to stick with the solid conductor. You see the copper wire that we attach to things like a battery, like a 9-volt battery. There's the positive and the negative. And you attach wires to connect something, like a lamp. Sorry, but I'm not a very good drawer. Okay, I can't draw very well. So, a lamp. We're going to study this case, okay? The flow of currents in solids. In solids, it's always electrons. There are some free electrons that can flow in an orderly fashion, like water in a tube, you know? And this is the point where you start thinking, okay, so it's like water flowing through some pipes. But something has to push this water. You know, like in a water system, there's a force, that pressure is some kind of pressure that pushes the water through the pipes. What pushes these electrons to form a current in an orderly fashion? What kind of force does this? That is the next concept we're going to study, which is the voltage. Voltage is the energy necessary to force this current flow through a conductor. It's a potential energy. Sometimes we define it as the difference of potential energy between 2 points. This will be clear as these videos go. So in order to push this energy, to push these electrons, we need some force. The force is the voltage. So if you live in the US, for instance, you have in your outlet, there is an outlet here. I don't know how to, okay, it can be like 110 to 24 volts. A simple battery, I'll try to draw a little better. This is a 9-volt battery. Okay, there it is. Okay, a car battery, just kind of big square box thing. You see, they have these different measures of volts. The stronger the voltage, the stronger the current flow in a conductor. Okay, it's as simple as that. So we know what flows through the conductor, and we know the force that pushes it. But how much current can go? You may think, well, so what limits the amount of current that can go through a wire? Because if we're going to this water analogy, like water in a pipe, there is a limit to how much water can pass. It's the diameter of the pipe. So in a electrical wire, is it the wire? Not particularly, not exactly. What it is the other components of the circuit. They exert some kind of a resistance to the flow of electrons. So what fixes this amount is this resistance some components in the circuit may have to the flow current, which brings us to the next topic, which is impedance. Many people learn the word resistance. Okay, it's underlined here. Many people learn this word first, resistance. But I think of it as an incomplete definition. As we're going to see later on, the complete definition to resistance to the flow of electric currents across a conductor is impedance. And for now we're going to use this word throughout the course. So let's say we have a battery here. Let's see. Really square battery, really nice. It has a plus terminal here, it has a negative terminal here. It's a 9-volt battery, and we have these wires. The idea of every circuit, to make it do something useful, is that we want to connect the positive to the negative in a way that makes something useful. So you may think, well, what happens if you just connect it? Just take a loop of wire and connect the positive to the negative. This is not good. This is bad news. This is not good. In 99% of the situations we do not want to do this. Okay, this is the definition of what we call a short circuit. There is no resistance between the positive and the negative terminals of the power supply. This will create a flow of electrons from positive to negative, and this flow will be as strong as possible. Every single electron that can go to the other side will try to do it at the exact same time. And there are billions and billions and billions of electrons, in a wire. In a small 9-volt battery, there are literally billions and billions of electrons. If they all try to go at the same time, the wire won't be able to keep up. The wire will melt, catch on fire, it will burn. The battery itself may become damaged. Okay? We do not want to work in these situations. Okay? We never want to connect directly the positive and the negative terminal of some power supply with no resistance in between, no impedance in between. There has to be some kind of impedance. Okay? So let's try to make a more realistic circuit. Let's try to light a lamp. So again, we're going to make a square with the positive terminal here, the negative terminal here. Again, we have a 9-volt battery, but this time we're going through a battery. Oh, I'm sorry, not a battery, a lamp. A lamp, and it glows. The lamp, this filament, the kind of the lamp that glows, those old lamps, not these LED, new kinds of lamps, those incandescent light bulbs like the ones Edison created, they have some kind of resistance to the flow of electric current, and this flow is proportional to the resistance. Okay, inversely proportional to the resistance. So this brings us to what we call Ohm's law. So Ohm's law is basically that the voltage equals the resistance, the impedance of the circuit or component times the current that passes through it. And with this definition, you can go to the other formulas. You just rearrange the variables. This to find the current, I is the current, and this to find the resistance. So you see in this formula here, the second one, I equals V over R. If R is 0, which is mathematically impossible, okay, but you see that it is in the denominator of the operation, which means that as resistance gets lower and lower and lower, the current goes higher and higher and higher. That's why you have a short circuit when we just connect it together, connect the two terminals together. Okay. Now, when we have something like this, something like the second circuit, we have some resistance here. Let's call it R. Now, this is not a short circuit. This is a functional circuit, and this is good. Okay. And the last definition we need to know is power, which is basically the amount of energy consumed or generated by the circuit and its components. Every circuit mostly consumes some kind of energy, converts it to something useful. That's what happens. It takes the energy of the flow of electrons. Every time electrons flow in a solid conductor, they heat up. And we use the energy of this heat, of this movement of electrons, we try to use this energy to something useful. That's how it works every time. So we can either consume energy or we can either consume energy and waste it as heat, just so we can make heat, like it happens in showers. That's the basic idea of a shower, to take energy and just create heat with it. Or we can take energy and convert it into something useful, like creating light with a lamp, creating sound, creating, transmitting signals, creating voice over long distances, over a wire, over a radio. We transform the amount of the energy we have. We can either consume, waste, or transform. And all this energy used by our circuit is what we call power. It's a really simple definition. Really simple definition. Okay. In every circuit, in every component, power simply equals voltage times the current. Yes. So let's say we have a car battery. See, we have a car battery right here. It's really pretty car battery. Okay, not so pretty. A 12-volt car battery, and it's going to power something, some sound system, and this sound system will use 5 amperes or amps of current. So how much power can this sound system produce? Well, it's very simple. Just take the voltage and multiply it by the amount of current passing through it. So this is going to be 60 watts. Pretty simple, right? And here, let's just pause the video and try to fill in the gaps. The idea here is just try to remember what we have seen so far. It's a really boring, question. It's really simple to answer, but try. Whatever. In any case, try. Pause the video, try, and then see the answer. Okay. So the force necessary to push electrons through a solid conductor is the voltage. And these electrons flowing through the conductor create an electric current, which is a uniform and steady flow of electrons. It's orderly. It has an orderly fashion. Okay. And the amount of electrons that can pass through the circuit depends on the total impedance or resistance of the circuit. Okay. And the product of the voltage and current is what we call the power that is either consumed or generated by the circuit. Well, always consumed basically, but transformed to generate something else. Okay? In the next video, we're going to see the differences of the types of current: alternating current and direct current. Thank you for your time, and I'll see you next time.